Now I'd like to introduce you to the H-bridge and geared motor. We'll be looking at H-bridge principles, pulse width modulated speed control, and then the quadrature encoder sensor that serves as feedback for measuring speed and rate. This is the components that are included in the NI myRIO mechatronics kit. We have the Digilent PMOD HB5 H-bridge, and then we have this motor, gearbox, and encoder unit from Xiaoyangye. The encoder is on the back side of the motor. Also, this motor product is available from Digilent as the motor/gearbox product. Let's review the PMOD HB5 features. This is an H-bridge DC motor driver. It can work with motor voltages up to 12 volts at 2 amps, and you have the heavy-duty 18-gauge terminal block to handle the higher amperage. The board has direction and enable inputs and produces a pair of quadrature encoder outputs. Use a supply voltage anywhere from 2.5 volts to 5 volts for the H-bridge electronics, and 3.3 volts is recommended. Next, let's take a look at the geared motor features. It's based on a DC motor with carbon brushes. It works on voltages up to 12 volts DC. The white connector here is the JST style connector, and it's intended to work directly with the HB5. Here we have the gearbox itself. This is a planetary gearbox with a ratio of 1:19. The quadrature encoder is mounted to the motor shaft directly. This is a 2-channel quadrature encoder, and it produces 12 counts per revolution of the motor itself. So in between here we have the DC motor, encoder mounted on the back to the motor shaft, again 12 counts per revolution. The planetary gearbox is located right here, and the output shaft produces 1 revolution for every 19 revolutions of the motor. Now, for applications of the geared motor, for mechatronics and robotics applications, a motor such as this makes an excellent drivetrain for your robotic platform. The standard output shaft is designed to attach wheels. You can also use this for speed and position control. All right, let's get acquainted with the HB5 details by looking at a functional diagram. We begin with 4 MOSFET switches and the DC motor. The DC motor has the 2 terminals, M plus and M minus. M plus is the red line right here, and the black wire is M minus. Get those 2 on here. And already this shape tells us why it's referred to as an H-bridge. This resembles the letter H, and this horizontal structure, the motor, sometimes people think of that as being like the bridge. Green wire is ground. It's also the same thing as the ground on the terminal block. That's going to connect the 2 bottom MOSFET switches. And the brown wire is the other end of the motor supply. Call that VM. While it is possible to use the myRIO onboard 5-volt supply, it's more likely that you would use either an external supply or a battery pack. Remember that it's 12 volts maximum. All right, at the moment I have my 4 MOSFET switches in the off state. That means there's no possible way that current can flow through the motor. In this case, the motor is off and not moving. Now, if we'd like to get some current to flow, we can close 2 of the 4 switches. And for this particular current path, we have counterclockwise rotation when you are facing the shaft. Now, if we open up those switches again, the motor shuts off. If you'd like it to go in the opposite direction, you flow current from M minus to M plus. The motor is on in this case, but now the rotation is clockwise when you are facing the shaft. Very important point here. Do not enable all 4 switches at the same time. That amounts to a direct short from VM to ground, and that's very hard on the power supply. Now this signal, one of the control signals coming into the HB5, is called direction, or DIR for short. The direction control is attached to two of the MOSFETs, and then we have an inverter, or that is an inverted version of direction, to feed the other two MOSFET switches. This ensures that we have only one switch pair enabled. Only problem is the motor is on all the time. Add in these two AND gates with an enable signal, EN for short, and that's located right here back on the J1 connector. And the AND gates ensure that when enable is low, then the hbridge is off. You need to make sure that that enable is low before you change the direction. Now, to accomplish variable speed with this setup, use a pulse width modulated signal for the enable. The myRIO has an express VI built in called PWM for pulse width modulation, and it works like this. Viewing the voltage as a function of time, we see a number of pulses. Here's the pulse period. The pulses are high for a certain percentage of that period. We call this the duty cycle. Duty cycle is the high time divided by the total period. The average value of this waveform is the duty cycle times the amplitude of the voltage. Because the motor speed is proportional to the applied DC voltage, varying the duty cycle varies the speed of the motor. For example, if you had narrower pulses, the motor speed would be slower, and if you have wider or fatter pulses, then the motor speed would be considerably faster. Now let's take a look at the sensor mounted to the back of the motor. This is the quadrature encoder. Here we have a circular magnet that's mounted to the motor shaft. Here we have a pair of Hall effect sensors, and these are able to detect changes in north and south as the magnet spins by. These two sensors, labeled A and B, are located 90 degrees apart. Sensor A is the blue wire, and sensor B is the purple wire coming back from the motor. These sensor signals are fed back through Schmitt trigger inverters on the HB5 board, and that gives you some degree of noise immunity. These signals are available from the HB5 right here. The remaining two pins are ground and the supply voltage for the hbridge electronics. 3.3 volts is the recommended voltage. Now let's look at the quadrature encoder in more detail. Now we have a circular magnet mounted to the motor shaft. We have alternating north and south, a total of 6 poles or 3 pole pairs. As you rotate the magnet past both sensor A and sensor B, north, or north number 1, passes by the Hall sensor and switches the state from low to high. As you continue rotating the magnet, you encounter first north 1, then north 2, then north 3. Now at the same time, sensor B initially sees south number 1. Sometime later, north number 2 passes by, and so on. As you rotate the magnet from B to A, the A waveform leads the B waveform. As you rotate the magnet from A to B, however, that is reversing the direction, we find that B still is looking at south 1, but A is about to see south 3, having just finished working with north number 1. So A is going to go low for a little while. And what we find is that A waveform actually lags the B waveform. Now the NI myRIO encoder express VI, when you select the quadrature mode, it counts the edges coming from these A and B signals, such as 1, 2, 3, 4, and so on. And what you find here is that with the number of magnetic poles that we have 12 counts per revolution. The encoder express VI also indicates the direction of rotation. When A leads B, the express VI indicates counting up. However, when A lags B, it indicates counting down. Finally, let's finish up by getting a glimpse of how you could set up a speed or position control system using this equipment. We might start with a desired shaft speed or angle. We have a control algorithm that generates the control effort, and this amounts to the PWM Express VI output from MyRio that passes through the H-bridge on its way to the motor, and then you have the shaft speed and angle that we might call the process variable. The quadrature encoder serves as our sensor. The encoder Express VI translates those sensor waveforms into counts. The counts themselves could serve as angle or position. The count rate serves as a measure of speed. This information then is fed back to the control algorithm as the measured speed and or angle. The control algorithm then looks at the desired value, what it's actually doing, and then determines how much control effort is needed to bring the process variable in line with the desired set point. PID control is most common for this application. PID is an acronym for Proportional Integral Derivative Control.